Good morning or good afternoon, everyone. My name is Ranjit, application engineer with Bloodless Design. I'll be your host for today's webinar, Identify and Fix the Inconsistencies in Electronic Systems Requirements using Dynamic Simulation. The major reason for taking up this particular webinar is to understand the kind of problems the inconsistencies can cause later in the design process, or it could be a success of a particular project itself. If you notice, nearly 70% of success of a particular project is purely depending on how exactly the architecture has been selected and the kind of workload analysis and the kind of uh, early architectural analysis that you consider or you conduct to be able to have a highly successful specification for the implementation system. And also the inconsistencies can cause a lot of problems either in terms of performance related issues, or it could be power related issues, or it could be a successness of a particular product itself. So today we'll be going over few items, understanding how exactly these inconsistencies can be identified and how we can fix these inconsistencies early in the design phase using Visual Sim Architect. Before getting started with today's webinar, I would like to go over a few logistics details. You will actually have a control panel, something like this, on your desktop right-hand side. There is a chat window. If you come across any questions, please post in your questions in the chat window. We have people in standby and they will be answering your questions. And also I'll be taking up these questions during Q&A session as well. So here is a quick overview for today's webinar, and I'll be starting off with trying to understand what are the type of requirements that we would really expect to start off with a system development, and then what would be the kind of inconsistencies that can be present in a requirements itself. Either it could be from a customer or it could be from the development team itself. And also we will try to understand how exactly, what are the different ways to identify inconsistencies in the design requirements itself. And then we will try to understand how exactly these inconsistencies can be identified and fixed using a dynamic system simulation using Visual Sim Architect. So I'll be going over a few demo examples as well to give you understanding about how exactly these dynamic system simulations will actually help you to capture the inconsistencies itself. For those of you who has not heard about Bloodless Design, we are a Sunnyvale, California-based systems engineering company, and our major product area is towards aerospace, defense, automotive, computing, and network and semiconductor systems, all the way from the systems that includes a very detailed cycle accurate level details of a particular memory subsystems or a processor. It can actually go up to a complete aircraft level, or it could be a complete intra-vehicle or inter-vehicle network itself. So you can actually model, simulate, and analyze architecture for these different type of application domains. And we have over 55 plus customers worldwide distributed across different different industries and different level of applications. And our major product is called Visual Sim, which is a graphical and hierarchical modeling and simulation environment. And I'll be showing you some of the demo examples using this product itself today. So the major idea behind our product and the kind of services that we provide is to make sure that the selected architecture is meeting all your requirements, either in terms of performance, power, reliability, or functional correctness. So what exactly happens if there is a kind of inconsistencies in the requirements? What kind of problems that you could anticipate out of these kind of problems? So one thing is that you could see a kind of unpredictable system behavior. For example, in this case, what I have here in the graph shown here, I'm actually looking at the execution of different ECUs on an automotive platform. So I'm looking at execution or behavior of of two ECUs with a certain set of workloads. In this case, I have considered uh, one benchmark workload here. And then with a different set of workloads, what I have seen over here is the behavior of this ECU execution is completely different. So one thing is that you may actually have problems, for example, whether this particular problem or unexpected behavior of my processing platform in my automotive platform is because of the hardware architecture, is it because of the software? So these kind of problems are the kind of questions you would actually come across. And if you come across these kind of problems as early as possible in the design process, then it is very good. But if you come across these questions or scenarios later in the design process, once you have implemented, once you've written your application software, and once you're having your first prototype with you, then the amount of effort and the kind of time that you're going to invest on identifying and debugging these kind of problems would be extremely high, and also it's not a kind of cost-effective solution as well. So we need to understand and capture as much as possible fault scenarios and unpredictability in the system itself. That could be because of lack of information that is communicated by the requirements team, or it could be the lack of communications that is passed on from the system development team itself. So these kind of problems must be identified as early as possible, right? So the kind of requirements that you could come across would be can be classified into mainly two sections. One is that the requirements that is being shared by the customers. So it will be in a kind of plain statements in natural languages. So you could actually get it from an Word document or something like that. And in addition to that, the requirements from customers may include the diagrams of the proposed system itself. So how exactly the customer is looking for this particular system. And then he may have or she may have some information about the detail or how exactly the kind of performance things that they are looking for. So the third scenario is very less, I would say, but the first and second scenarios are pretty much common in most of the cases. If you look at the system designer side or perspective, requirements can be a kind of design document, so in which you actually have defined a kind of step-by-step information on what exactly the full system would look like, and how do I break my system into multiple subsystems, and what are the kind of algorithms that would be actually required to arbitrate a particular transaction out of a bus or something like that. And in order to gain those details, you may need to have detailed simulation models that are constructed in System C or C or C++ or something like that. And also you may need to have a very detailed behavior flow that tells you what really happens if you press a particular button, and what is the impact of that on the functionality of my system platform itself. So those are actually coming under your workloads and use cases scenarios. So you need to capture as much as details upfront to make sure that the selected architecture is meeting all these defined requirements over here, and is error-free. So if you look at the inconsistencies again, what are the possibilities for inconsistencies in the requirements? One thing is that the design requirements can actually change during the requirements gathering phase itself. So in your first meeting, you would actually have a certain set of defined use cases or workload scenarios, but in the next time you may actually listen to a completely different requirements phase. And also in addition to that, you may actually have redundant and conflicting requirements. This is one of the crucial part of the requirements capturing, and this can be seen in most of the scenarios as well. For example, you may actually have an avionics system in which the data transfer of about 20 gigabytes per second across all the modules in the chassis, but the permitted power is about 200 watts of power. So if you look at the amount of data that you're transferring across the system module, the amount of power consumption that you're mentioning over here would be very less. So this could be a kind of very conflicting or kind of confusing scenario to select an architecture itself. So you need to have more information on what exactly it is, or is there any kind of inaccuracies in that requirements capturing itself. And also, in addition to that, the other scenario would be if the input data rate is about 2 gigabytes per second, while the post-processing needs to be stored in a flash memory. And if you look at the access time of a particular flash memory, it could be at the level of read and write latencies of about microsecond range. So this tells you that working with this particular requirements is highly impossible because the data rate is extremely high and the processing time is not good enough to process that much data. So you may end up losing the data or something like that there. And also, in addition to that, the major reasons for inconsistencies in the requirements is incomplete information about a particular behavior or an execution sequence of a particular task itself. So you may not really know what really happens after pressing a button in your mobile phone, and that may actually cause a lot of problems in terms of how exactly I need to build up the complete application sequence to able to get it working. And also, in addition to that, you may not really have detailed information about how a particular algorithm is implemented, whether I need to implement it as a software part of my system, or do I need to implement it on an FPGA or an ASIC or something like that. So those scenarios, for example, if you are going to implement it on a processor, you may actually require a lot of CPU cycles to process to implement that particular algorithm itself. Whereas implementing it on an FPGA requires more cost because you may actually have a highest performance there, but cost-related challenges could come up at that particular stage as well. So you need to have very detailed information about how exactly the system must be implemented and what exactly the sequence of activities that are going to happen as well. So if you look at the type of inconsistencies that we can think of in terms of system requirements, we can actually classify this into 6 parts of it. One is that timing related stuff. So you don't really know how much time a particular memory that is defined in an specification is going to take. For example, let us say you are working at a low power device requirement and you're actually using a DRAM which is running at about 200 megahertz or something like that, and you're expecting a particular data rate or throughput from that particular memory, but you're not going to get that. And you will actually end up in a kind of processor stalls, or the kind of success of that particular application is completely gets into vanish. And in addition to that, confusions related to technology parameters itself. For example, it could be bytes versus bits, or channels versus how many lanes that you're going to use and things like that. So those technology-related confusions may also cause a lot of inconsistencies in terms of system requirements as well. And in addition to that, one more crucial part is connectivity. So if you're actually working with, in terms of multi-board system platforms, you may need to consider how exactly multiple processing boards are connected. For example, let us say you have about 4 high-performance computing systems that are connected across a rapid I/O switch. So you need to understand whether these high-performance computing systems are really accessing any external memory, or they're actually accessing the memories that are inside that particular rack itself or something like that. So you may need to understand, or you may need to have more information on connectivity between multiple subsystems and multiple components in the system as well. And in addition to that, you need to have information on energy consumption as well, because if energy consumption is a crucial factor, for example, if we consider an avionics platform or any handheld devices, the power consumption of the system is highly crucial. And even though the performance is very good and meeting your requirements, but you can't run it for more than 30 minutes or something like that, then the whole purpose of constructing or creating that particular system itself is of complete waste. So you need to consider your timing parameters and energy related parameters and the availability of the resources as well while making the specifications to make sure that the requirements are going to meet at the end of the uh, product implementation. And in addition to that, inconsistencies could include how exactly the system is going to respond for a particular type of faults. For example, let us say you have two redundant networks that are connected across AFDX platform or something like that. You want to understand what happens if a particular link goes down and what would be the impact of that fault on the complete system performance. So you may actually have another link up and running all the time, but impact of sending too many transactions across that particular link may actually cause contention related problems, or it could be your link bandwidth can actually drop down significantly as well. So these are the kind of different type of inconsistencies that you could actually expect at system requirements. And this is not a kind of exhaustive list, but here we have captured a few important list of inconsistencies here. So in order to identify these inconsistencies, there are about possibly four different ways. One thing is checklist basis. It could be based on questionnaires. So checklist in the sense you might have already worked with a similar system in the prior project or something like that, and you would actually have a certain set of checklists to comply with, and you can actually go ahead and check all those things. But if you see here, the checklists and questionnaires are more of correction of the language itself. It could be a correction of a particular technology parameter that you have used, and requirement in terms of completion of a particular task and things like that. But this may not be really detailed information, but it will be limited to it will be limited to language specific inconsistencies, corrections, and things like that. And in addition to that, if we look at a probability based models, so probability based models will be extremely hard to create, and also they'll be limited to identifying the possibilities of the occurrence as well. And you may not really able to capture all the error scenarios that could happen with a incorrect processor, incorrect behavior flow or something like that. So the other option is selecting a simulation-based approach or modeling and simulation. So simulation-based verification actually provides you a complete coverage of all the viable use cases and accurately measure the timing and power consumption of your complete system platform itself. And also you'll be able to understand how exactly the transactions or data is moving from one block to another as well, and also the amount of time your arbitration algorithm has taken to transfer a particular data from a particular channel, and also correctness of an algorithm itself. So you can actually conduct varieties of analysis to make sure that the inconsistencies are identified and eliminated using a modeling and simulation environment. Okay, so the major reason for selecting modeling and simulation as the best way to identify the inconsistencies is because you'll be able to get a highly accurate specification early in the design phase, and you don't really have to spend a lot of time later in the design process or later during implementation phases to be able to identify the inconsistencies in the platform itself. So how exactly modeling and simulation can actually help in identifying the inconsistencies? So you will be able to capture your design requirements at different level of abstractions based on level of details that you have. let us say, for example, you're creating a memory subsystem in which includes a bus as well as part of the system, and you don't really have enough information about which is the bus arbitration scheme that you're going to utilize based on how many number of masters that are going to be there in the system platform. And you can actually keep that as a very higher abstraction level, keeping certain amount of delay for that, and explore remaining part of the systems. Okay, and that actually tells you that that the arbitration is the module that needs more information, and you need to incorporate the arbitration related stuff and try to explore the system requirements once you have that ready with you. And in addition to that, modeling and simulation enables you to create virtual models of your hardware, software, algorithms, control logic, and network in a single environment itself. So which means evaluating your system platform, considering all the factors that are going to affect performance and success of a particular project is possible with modeling and simulation. And by this, you'll be able to capture the inconsistencies associated with different modules or different parts of the system itself. Okay, and as you can create incremental models of the proposed system architecture, you can start off from very little information, and you can add up more details as you go along during the project development phase. So that actually provides you more information or provides you sufficient space to conduct analysis and validation of the system properties with the level of details that you have with you. And also, as you are working with modeling and simulation, you can introduce varieties of different faults as well. Because you are working with a virtual system platform, you can introduce faults in terms of hardware architecture, or it could be in terms of software architecture itself, or breaking a link between one subsystem to another subsystem and trying to understand what is going to be the impact of that network failure on the rest of the system platform itself. Okay. So as I mentioned earlier, in order to have a successful or a highly accurate specification of a proposed system architecture, you need to have or you need to consider at least two factors. So one thing is that, are you considering factors such as power consumption and performance related stuff and availability of the resources itself. So these three factors must be considered at the same time, and the architectural components must be selected by considering these three factors. For example, if you say you're considering ARM Cortex A9 processor as opposed to A15, what are the power benefits, what are the performance benefits, and the footprint benefits that you're going to get out of that particular selection of that particular processor platform itself. So in addition to that, you may have to consider, or if you are working with real-time applications or hard real-time applications, then you need to make sure that all the tasks that are going to run on the proposed system platform is going to meet all your timing deadline. So you need to make sure that any particular task is not overflowing or going to a next time slot or something like that because of non-availability of a resource, or it could be because of contention in a particular resource itself, or it could be based on non-availability of an acknowledgement from a particular subsystem itself. So you need to make sure that the deadline requirements for the software and for the hardware architecture that you have created is going to meet all your requirements as well. So considering these different factors that we talked about, we have actually assembled the tool Visual Sim Architect, which is a highly graphical and hierarchical modeling and simulation platform. And we also provide you a list of library blocks, which includes stochastic and cyclic rate level libraries, enabling you to create models of your proposed system architectures to identify the kind of bottlenecks and inconsistencies early in the design phase by creating models of your hardware, software, network, and traffic, and things like that as well. And also, if you have any other modules that are defined in C, C++, or System C or something like that, you can actually bring in those interfaces directly into Visual Sim Architect. So looking at the addressing the challenges associated with inconsistencies, so we actually focus majorly on ensuring the optimal sharing of the resources itself, whether it is a processor or it is a memory or it is any bus or things like that, or it could be an FPGA. How do I actually utilize my available hardware architecture to run the set of applications that I have with me to get a better performance versus power consumption? Okay, and the problems would be associated with multi-threaded applications, or it could be parallel processing of the tasks as well. So in those scenarios, the kind of problems that you would definitely expect is at the level of memory access. So you may actually have the previous data available or the kind of outdated data available in the memory. So you need to make sure that you're selecting the right cache replacement algorithms or algorithms to make sure that you have the latest data available in the address that you're looking for. So you can, with Visual Sim, you can, you will be able to model such type of accuracies of the system platform as well. Okay, and in addition to that, one of the very crucial aspect of early system explorations, or to make sure that your specification is going to meet your requirements, you need to make sure that the set of applications that you're running, that you're trying to run, is able to run with multiple hardware configurations. So the reason for doing that is after a few years, your hardware component could be obsolete, and if you want to replace with a particular hardware platform, you must be able to run the software applications without any performance problems or without any functional problems and things like that. So the hardware architecture and the software behaviors must be validated to make sure that the system is going to work for your current requirements as well as your future requirements later in the maybe 5 years down the line or 10 years down the line. And in addition to that, the kind of problems that you can address with Visual Sim is defining the communication network topology and making sure that the network latency is not exceeding your requirement or the kind of specifications what you might be having with you. So you can capture or you can define your network topology, which is connected with your processing resources or storage devices, and make sure that the end-to-end latency for a particular task from one node to another node is meeting your requirements as well. Okay. So at this point, I would like to go over to Visual Sim to give you a feel about how exactly the simulations would actually provide you facility to capture these different factors. I'm going to go over to Visual Sim now. So the model that you're looking at right now is a system with two CPUs and a DSP and an I/O. And I/O can be an Ethernet interface or it could be an USB. And at the bottom, I have defined my applications as a sequence of tasks that are going to run on the target platform. So here I have the processors running at 400 megahertz and bus 1 running at 400, bus 2 at 200 megahertz. The way how it works is this source block transaction generator will actually trigger the transaction for the applications itself, and it tells you what is the interval between a particular arrival of that particular task itself. And these blocks are actually mapped onto the target platform by node mapping. So if you need more information, you can actually subscribe to our training program to gather more information on the terminologies that we use. So here what I'm going to do is I'm going to run the model to try to understand what is the end-to-end latency that I'm capturing or getting from the applications that I'm running. So here I can see that my end-to-end latency capture for application 2 is about 1.5, and utilization of the resources, CPU 1 is utilized about 92%, whereas CPU 2 is utilized about 55%. So this tells you that you're running too many tasks on your CPU 1 while you're running only few tasks on your CPU 2. So you can actually shift about 20% tasks from CPU 1 to CPU 2. So this is a kind of information that it provides you to make sure that the distribution between resources are meeting your performance requirements and you're not overburdening a particular resource itself. Okay, and the kind of inconsistencies that we actually enable you to identify and eliminate includes changes in the system configurations. As I just showed you, you can change the system configurations and try to understand how exactly the system is going to behave. For example, in the previous example that I showed you, here I was actually running my bus 2 on 200 megahertz, and my maximum latency here was about just below 1.5 microseconds. So if I increase the clock speed of bus 2, what would be the kind of latency that I could expect? So if I look at this particular model, earlier I was getting around 1.5 microseconds. By increasing the clock speed, I would actually expect the latency to come somewhere close to 1 microsecond or something like that. So if I run the model, I can actually see here that most of the tasks are actually getting executed under 1.2, whereas there are a few tasks that are actually going above 1.5 microseconds. So even though you're running your systems at a higher clock speed, your end-to-end latency is quite high. So this could be the problem with your CPU because you're running your CPU at a low clock speed, or you need to change the selected processor itself. So this kind of information will actually enable you to make sure that the problems can be identified and eliminated at early stages of the design process. So in addition to that, you can make sure that the tasks that you're running, if you're running real-time or hard real-time applications, then you can make sure that the timing deadlines are met without any rollover to the next slot or something like that. So to give you an idea or an example, here I have an example system platform for a display processor for an avionics system, and in this case I have the interfaces that are connected with AFDX traffic and ARINC 825 traffics that are coming in, and I have my ARINC 653 scheduler, which is actually I have defined over here, and I have defined my processing unit at the top over here. So for ARINC 653, in this case, I have about 6 partitions, and I have provided the time slots associated with each partitions as well. For example, the spare time is about 1.5 milliseconds, which means the tasks that are going to run on my spare partition must be completed before 1.5 milliseconds. And if it is taking more than that time, you need to either consider it as a failure task, or you need to just drop it off, or you need to make a note and take the next partition task, and you can take it and execute this particular preempted task later in the or maybe in the next frame or something like that. So what I'm going to do is I'm going to run the model. So what I'm capturing over here is to try to understand how many tasks that are being successfully executed without exceeding the timing deadline. So the blue one is actually the tasks that are actually completed within the timing deadline, which was assigned, and the red one is the one that are actually taking more time than expected. Also, if you look at the end-to-end latency here, there are actually the tasks that are taking more than 3.5 milliseconds as well, whereas the maximum time that we have, the slot we have provided is only about 3 milliseconds of time. So this actually tells you that because of non-availability of the resources or increased memory access related problems, you would actually expect the unexpected behaviors. And if you look at which VM or which virtual machine or which partition is consuming the highest latency, here you can see that the 6th partition is actually taking too many CPU cycles. and that is causing the increase in latency itself. So you can actually provide more focus into this particular or the type of applications that you're running in this particular partition and make sure they are meeting your timing deadline requirements as well. Okay, and in addition to that, what else you can do is you can make sure that that a particular module consumes most of the available power itself. So, which means you're not consuming power at a than what you're expecting, and making sure that the heat dissipation is under control itself. Okay, and in addition to that, you can identify and eliminate the problems that are related to a failure in network link itself. So what happens if the network link goes down between two subsystems? So I'm going to show you a very simple example for this scenario. So here I have a system with about 5 or 6 nodes. Here I have 2 source nodes, and in the right hand side I have 2 destination nodes, and in between I have some routers and switches related to that. And in this, what we are doing here is we are actually going to remove the link between node 3 and node 5 at a certain timestamp, and we are going to add it back and try to understand what is the impact of removing a network link on the complete system performance. So when I go ahead and run the model, you can actually see here that adding a particular additional link is actually causing increase in latency over here as well. So you may not really need that additional link, or the link processing is too high, and because of that the end-to-end latency went up all the way from 0.5 or 0.5 milliseconds to about 3 milliseconds of time. Okay, and in addition to that, you can do a kind of traceability as well. So from which node or from which block you are actually starting the transaction, and what is the hop details and the trace details for the complete transactions that are going through in your system as well. Here we are actually saying that node 1 received a request from a particular processor node, and it actually went over to node 3, node 5, and the MUP, which is actually on the other side of it. So as I mentioned, please feel free to post in your questions in the chat window. I can actually go a little slower and answer those questions as well. Okay, and in addition to that, you can identify and eliminate inconsistencies related to error detections based on error probability as well. You can model a different set of error probabilities in Visual Sim and simulate your system platform with a given set of error probabilities, and make sure how exactly the system works and what are going to be the impact of those added error scenarios on the system performance and functionality itself. Okay, and in addition to that, one of the very common problem or the common reason for inconsistencies will be replacement of a particular module. So when you started off with designing a particular system, you might have selected a particular component or a particular subsystem for doing a specific job. And after spending few days or few months of explorations with the system, you might have thought about changing a particular component or a particular subsystem itself. And you need to make sure that what is going to be the kind of problems that is associated with replacing a particular module. Either it could be at the implementation level, or it would be after implementation as well. So what is going to be the kind of impacts that it is going to cause, and whether it is going to still meet your performance requirements or not. And also you can make sure, or you can understand what is going to be the impact of absence of a handshaking message on the success of your particular product as well. Okay, and in addition to all these design and exploration related problems that are talking about inconsistencies, there are few inconsistencies that must be addressed at the communication level as well. For example, the way how you're defining the specification of the product itself or the system itself, and the type of terminologies that you use to explain the concepts, and also the communication or the correctness of the flow itself, which is defined in the document. And all these factors must be considered and must be defined in a specific way and in a correct way to make sure that the communication related problems are will never come into picture. So we actually enable you to generate a very detailed documentation for the project that you're working with, including the block diagrams and parameters that you have selected and the kind of reports that you're generating. So all the reports will be actually generated into a HTML format, and you can share that with the rest of the team. They might be sitting in your same office, or they might be sitting in a different country, or things like that as well. So the communication related problems can be easily addressed with the documentation capability of the simulation models as well. So here's the model that I actually talked about, and this is actually a display processing unit. So if you look at over here, the complete model has been assembled using barely 6 to 7 blocks, and almost all these library blocks are pre-configured, and you just have to set up a few parameters to it. For example, if I go back to this particular model, if I look at this DRAM over here, I have already provided certain set of parameters. For example, what is the speed of the memory that you're running, and what is the size of the memory, and what type of memory it is, whether it is a DDR, SDR, or something like that. And you can define your access times related stuff. Configuration of these blocks are very simple and self-readable, and this takes very little amount of time to create your simulation models itself, and the time that you're saving with model construction can be effectively utilized to analyze the system platform to make sure that all the inconsistencies or all the unpredictable behaviors can be captured as soon as early as possible in the design process. Okay, and here's one more interesting demo examples that I wanted to talk about is understanding the behavior or understanding the inconsistencies in the coils of a permanent magnetic generator itself. So in this case, this is a module that is actually a part of an integrated vehicle health monitoring system for an aircraft. And in this case, we have a PMG, and you have the A to D converter, AC to DC converter, and then you have multiple loads that are connected to the system platform itself. And what we are doing over here is we are actually trying to understand whether the PMG is able to supply sufficient power for the loads that are connected. So to make sure that the loads are provided with sufficient power, we actually have a battery module as well, and that keep on providing the sufficient amount of energy to make sure that the system is not going into failure state. So in this case, if I go ahead and run the model, so what we are capturing over here is trying to understand how much power is being utilized by different loads, and also the error message. In this case, I'm actually capturing to make sure to understand that after a certain time period, because all the devices are consuming power, there is not sufficient power available in the system itself. So the permanent magnetic generator, or PMG generator, is not generating sufficient power, and because of that we are actually seeing that battery power consumption is getting down, which is actually about 5% of the total battery capacity what we had. And that tells you that you need to shut down non-critical devices to make sure that as a system, your system is not going to go into a failure mode, but it will be working in a kind of restricted mode. Okay. And as I mentioned, the other part of it is considering the failure of a particular network link and understanding what is the what is the impact of removing a particular network link on the complete system performance. Okay, so in addition to, or in order to bridge the gap between pre and post development challenges, so we actually provide a tool called Visual Sim Explorer, which is a web-based simulation model in which uh, you actually export your simulation model into a detailed documentation along with a executable model which can be accessed right from the web browser, and you're going to ship your specification as a combination of your documentation plus simulation model in a single document. So the user is not going to install the tool, or they don't really have to learn the tool or anything like that, but they will go through the documentation what you have written, and they will run the model, try to understand what are the kind of reports that they are expecting and what is coming out of the simulation model. So which is something like you're providing a virtual system platform to the client or a supplier to make sure that the requirements and the specifications defined are in sync with what your development team is working with. Okay, so to conclude this webinar, early system modeling and simulation actually enables you to identify and resolve the inconsistencies in the design specifications and also in the requirements that you have captured. And also it helps you to kind of ask right questions to the concerned people to gather more information on the specification or the requirements itself. And you can make better architectural decisions based on the quantitative results, and instead of a kind of guesswork or something like that. So you provide the parameters, you simulate the model, and make sure that everything is in sync with what you're expecting. And as you know that more than 70% of faults or the problems can be actually captured at early design phase, and the time that you're going to spend is within 20% of your total project development time, which means you're going to make sure that the selected processor, selected specification is going to meet all your requirements without any problems or without any need to come back to the initial phase of implementation work or something like that. Okay, and in addition to that, the kind of explorations that you are going to conduct make sure that the performance, power, and reliability metrics are meeting for the set of requirements or for the set of specifications that is actually defined to have a successful product itself. So this concludes this webinar, and now the session is open for questions and answers. And I can see that most of the questions are being answered in the chat window. And if you have any questions, please post in your questions in the chat window.